In modelling atoms getting happy, we've applied what is often called the octet rule or the octet/duet rule. First of all, metal atoms want zero valence electrons, so therefore, of course, our alkali metals all have that one valence electron. They lose it to get down to zero valence electrons, just like the noble gases. Alkaline earth metal atoms want to lose those two valence electrons to get down to zero. So that was what we were applying when we were making cations, certainly of the S and the P block, ignoring of course the inert S rule, and it's also what we applied for certain of the cations of the early transition metals, which, if you remember, could not only lose their S electrons but could also lose all the way up to however many D electrons they had. The octet part comes for non-metal metalloid atoms which want 8 valence electrons, and we applied that idea when we saw that, for example, the halogens gained 1 electron to become a 1- cation, giving them from 7 to 8 valence electrons. The duet part is poor old silly hydrogen, can't count as far as 8, only wants 2 valence electrons, and of course if we look here, that's because hydrogen has 1 valence electron. One more will take it up to being helium. Now what we then saw was that when you have a metal atom, which of course wants to lose electrons, combining it with a non-metal or metalloid atom that wants to gain electrons, you can have that electron transfer, and that's a terrible application of that phrase, but it will work from now, from the metal losing electrons, giving them, so to speak, to the non-metal, so it gains electrons. Cation and anion attract each other, making an ionic compound. Now, I know less than 1%, less than 0.1% of compounds are ionic compounds. Much more common is where you have non-metal and metalloid atom with another non-metal or metalloid atom. All of these, of course, want to gain electrons. They cannot gain electrons from each other, so what they do is they share electrons to make a covalent compound and pretend that they have gained those electrons. Before we delve into how atoms will share electrons, let's augment our knowledge of how to name compounds, name simple compounds, by learning how to name a few covalent compounds, in particularly binary covalent compounds, those that contain two different types of atom, and of course both types of atom are going to be metalloids or non-metals. Now, the way you do it is you name it in two parts. First of all, every name has a prefix, and then you give it the name of the particular atom. Okay, so we're going to have, because we're talking about two types of atom, we'll have a prefix and a name of an atom for each type of atom. So two prefixes going with two names of atoms. Let's focus on the name of the atom first. Okay, you always take the first atom, being the one further to the left on the periodic table, and hydrogen, being weird again, is above nitrogen. If both are in the same group, you take the one lower down. You use the atom name for the first atom, you use the "-ide form of the name for the second atom. Now that's a little confusing, but very easily illustrated. Let's start off with phosphorus and sulfur, P4S6. Okay, well, there's phosphorus and sulfur on the periodic table. Phosphorus is to the left of sulfur, so that means that phosphorus is the first atom. Okay, the one further to the left, and sulfur is the second atom. We use the atom name for the first atom, we use the "-ide form for the second atom, so the name of this will be something to do with phosphorus sulfide. B2Cl7, Br2Cl7, excuse me. So here's Br and Cl. Br, both of them in the same group. So we're going to take Br as the one lower down, that's the first atom, so we'll have bromine, and then the second atom we'll have in the "-ide form, so it'll be chloride. So this is some form of bromine chloride. Finally, SiH6, okay, well, Si is to the left of this weird place where we put H. Okay, hydrogen goes above N when we're talking about naming, so Si is left of that. So that means this will be the first atom, so it's a silicon. H is the second atom, so it will be a hydride. So thus, this is some form of silicon hydride. Okay, so when you're naming these binary covalent species, you've got two atoms, you have to decide which order you're going to put the atom in, and the one that you put second you do as its ide name. Second part is we put the prefix in. Prefix just refers to how many of that type of atom. So here's the little series you need to learn: 1 mono, 2 di, 3 tri, 4 tetra. Those are the weird ones, and then from 5 onwards you get to the ones you're used to: penta for 5, hexa for 6, and so on, up to deca for 10. That's as far as we'll go in this particular course. So now let's go back and revisit P4S6. We said it was a phosphorus sulfide. We have 4 phosphoruses, phosphori, so that's tetra. We have 6 sulfurs, so that's hexa. So it becomes tetraphosphorus hexasulfide. Bromine chloride, we had 2 bromines, so that's di. We had 7 chlorides, so that's hepta, so dibromine heptachloride. And then with the silicon, 2 silicons, di, 6 hydrogens, hexa, so disilicon hexahydride. A few little exceptions, weird rules. If there's only one of the first atom, you omit the mono. So CO2 is not mono carbon dioxide, it's just carbon dioxide. And then sometimes when you put the prefix with the atom name, it puts some vowels right next to each other awkwardly, in which case you just omit the vowel on the prefix. So for example, CO is carbon monoxide, not carbon monoxide, which of course sounds like a Scotsman trying to say it, or monooxide if you're not trying to be silly. So anyway, that's how we're going to name these compounds. As we go through, we'll apply those and give even more examples. A nice simple way to learn how to name them. The difference between ionic and covalent: covalent, you have to say how many of each type of atom you have there. With ionic, that is defined in terms of the charge of the ions, so it is redundant to say how many of each you have. In order to model and explain covalent compounds, it's convenient to draw so-called Lewis structures. Now, those of you who went through some GCSE, in particular A-level, you might have learned these as dot and cross diagrams. Dot and cross diagrams are hideous, they are disgusting. We are going to use Lewis structures named after Gilbert Newton Lewis, arguably the first great American chemist. So only for a Lewis structure, you just use the atom symbols of the atoms involved in a molecule, and then valence electrons, which you draw as a default as dots. You put these dots in the top, bottom, left, right of the atomic symbol. There's no particular set order. I saw one book that says you put the first one in the right, and then the second one in the left, and the next one, and that's bollocks. Okay, you just put them singly until you have 4 of them, and then pair them up. So let's illustrate that first of all with some nice simple atoms and ions, which you never actually really use. You use Lewis structures for covalent compounds, but you can at least see the principle. So a sodium atom, for example, has 1 valence electron. So we're going to have the symbol, which is Na, and a dot for that valence electron. Carbon atoms have 4 valence electrons, so we use the symbol C and 4 dots, and notice that you put those 4 dots individually before you start pairing them up. That's what I mean by that line in green. You put them singly until there's 4 of them, then you start pairing them up, as we would see, for example, with a nitrogen atom, which has 5 valence electrons. So we're going to have 1, 2, 3, 4, and then we put the 5th one as a pair. Whether we put that pair at the bottom, at the top, at the left, or the right, who cares? What's important is that for a proper Lewis structure representation of a nitrogen atom, there's 1 pair and 3 single dots. And just to wrap up with the atom part, chlorine, 7 valence electrons, so you're going to put 7 dots. So we're going to have 3 pairs and 1 single one. We can depict ions, although sometimes it's rather redundant to do that with monatomic ions. It does become very important for polyatomic ions, as we might see later on. So anyway, sodium atom wants to lose that 1 valence electron to make the sodium cation, which therefore by definition has 0 valence electrons. So the Lewis structure of this would just be Na with no dots, but just to indicate that it's a charge, if we're going to be correct with it, we'll put it in square brackets with a little plus sign. Chloride comes from a chlorine atom, in which that chlorine atom has gained one valence electron to give it 8. No big shocks as to where that would go. I've drawn it in red. That also is very naughty. There's no difference between this electron and the other 7 valence electrons, but I'm putting it there to illustrate where it came from. You're putting 8 dots around the chlorine symbol, and because it is an anion, you put it in square brackets with the little minus charge. So now let's discuss how to use Lewis structures or Lewis dot structures to illustrate covalent molecules. And we'll start off with one of the simplest covalent molecules, chlorine, or some people would say dichlorine. This is how chlorine exists in the elemental state. You don't find chlorine atoms because chlorine atoms are unhappy. You see chlorine molecules, these diatomic homonuclear molecules, diatomic, 2 atoms, homonuclear, same type of atom. Okay, so if we think of chlorine atoms are unhappy. They have 7 valence electrons. They each need 1 more. If I was doing this for a younger group, I would start talking about how one chlorine atom says to the other, give me an electron, I need one. And the other chlorine atom says, the heck with you, I need an electron, you give me one. What we'll do here is we will just illustrate the principle that if those 2 chlorine atoms get close enough to each other, then the nucleus of one can see the electron from another one. So they are effectively sharing these 2 electrons illustrated by these 2 dots here. So this chlorine atom has 2, 4, 6, 8 valence electrons. This chlorine atom has 2, 4, 6, 8 valence electrons. The fact that 2 of them are shared doesn't affect the overall count for each atom. So each one of them is happy. Now we call those 2 shared electrons there a covalent bond. And a lot of times we'll illustrate the fact or emphasize the fact that these atoms are sharing electrons and thus are joined together by drawing it as a line. This line showing that these 2 chlorine atoms are bonded together, and a line represents 2 shared electrons. Now the remaining electrons in this molecule are not shared. They are unshared electrons. They are non-bonding electrons. We will draw those as lone pairs. Okay, so a lot of times you will hear the phrase lone pair. That just means 2 non-bonding electrons sitting there on an atom. Chlorine atom wanted 1 electron. It could do it by getting that electron from a metal to make an anion, or it can do it by making 1 covalent bonds, taking 1 of its electrons, sharing that electron with another atom, which in return shares 1 of its electrons with the chlorine atom. Another example in which we will take everybody's favorite covalent molecule, dihydrogen monoxide, otherwise H2O. And if you have time, and you should do, pop around on the internet and look at all the fun little things that have been come up and supposedly given to people using dihydrogen monoxide instead of water, and illustrating how people don't learn fundamental chemistry. For example, this horrible substance dihydrogen monoxide should be banned because it is found in 100% of cancer patients, etc., etc., etc. Anyway, H2O, we have 2 hydrogens and an oxygen. Each hydrogen has 1 valence electron and needs 1 more. The oxygen has 6 valence electrons and needs 2 more. So how will they do it? Well, the 2 hydrogens will get close enough to the oxygen that the oxygen can see that electron from each of the hydrogens. Now it thinks it has 2, 4, 6, 8, and each hydrogen comes close enough that it is to not only sees its electron but 1 each from the oxygen, so each hydrogen believes it has 2. Draw that, of course, illustrating again the bonding pair as a straight line, emphasizing the fact that the oxygen is bonded to each of the hydrogens. Okay, again, hydrogen atom wanted 1 electron. How did it do it? It made 1 bond. Oxygen atom wants 2 electrons. How did it do that? It makes 2 bonds. Now, I could do all kinds of further examples, but before I do that, let's see if we can't generate a nice common rule, which I like to call common sense. And that is that if an atom wants X more electrons, if it's been sensible, it will make X bonds. We've already seen chlorine. Chlorine has 7 valence electrons, which means by the octet rule it wants 1 more. So by common sense it will make 1 bond. And so when you draw a chlorine atom, if it's going to be sensible, it will have 1 bond to another atom up here and 3 lone pairs. We've just seen oxygen. 6 valence electrons, so wants 2 more according to the octet rule. So it will make 2 bonds if it's sensible, and we've just seen that with water. If you have a sensible oxygen, it will have 2 bonds and 2 lone pairs. Continuing on, let's think about a nitrogen atom, or of course I could have picked a phosphorus or an arsenic, because whatever we say for each of these atoms applies to all of the other non-metals or metalloid atoms in that group. Nitrogen has 5 valence electrons, wants 3 more, thus sensibly will make 3 bonds. So if you see a sensible nitrogen atom in a molecule that you are drawing, and this is how you should draw most nitrogen atoms, it will have 3 bonds and 1 lone pair. Carbon atom has 4 valence electrons, wants 4 more, so we'll make 4 bonds. When you get into organic chemistry, if you ever draw a carbon atom that has more than 4 bonds, my colleagues will get very cross with you. Carbon atom will make 4 bonds and has no lone pairs when it's been sensible. And of course hydrogen got 1 electron, wants 1 more according to the DUET rule, thus makes 1 bond, and we just saw that in our water as well. Some more examples. Putting out little common sense rules up here. The etc. means all the other ones in the particular group. CH4, well, a carbon we draw with 4 bonds. A hydrogen we draw with 1 bond, and we got 4 of those. So how are we going to draw CH4? Obviously the carbon with its 4 bonds with a hydrogen on the end of each of those. PF3. Phosphorus is like nitrogen, it has 5 valence electrons, so 3 bonds, 1 lone pair. Fluorine like chlorine, 3 lone pairs and a bond. So we got 3 fluorines, each of which wants to make 1 bond, 1 phosphorus, which wants to make 3 bonds. Obviously the phosphorus with its 3 bonds, a fluorine on the end of each one. And a bit more complex, C2H6, carbon, of which we have 2, wants 4 bonds. And we have 6 hydrogens that want 1 each. Now, of course, if we were to just stick 1 hydrogen on the end of each one of these bonds, we'd have CH4, and we wouldn't have any room for the second carbon. Thus, you must have 1 carbon bonding to the other. When it does that, we have remaining 6 hydrogens to go in those 6 bonds. Thus, that is C2H6. Lots and lots of practice needed here, but they are just essentially little puzzle solving, almost like little bits of Meccano, if that's not dating me too much, putting these things together. We don't have to live with just single bonds. We can make what are called multiple bonds. For example, think of dioxygen, 2 oxygen molecules, each one of which wants to make 2 bonds and has 2 lone pairs. So obviously 1 oxygen comes to the second oxygen and they make a bond, which we can depict either like this or like this. Okay, so the oxygen's making 1 bond, but now they still each want to make another bond. They've still each got a hanging electron that they would love to use to make a bond. So what they're going to do, they say, well, if making 1 was good, making a second one is probably twice as good. Okay, now when we look at this, each oxygen has got its 8 valence electrons. Each oxygen has made 2 bonds and got 2 lone pairs, so they're still sensible. But now we've got 2 lines in the middle, because it's not just 1 pair of electrons, it's 2 pairs of electrons, 4 electrons being shared. And we call that a double bond for obvious reasons. Nitrogen, N2. Now you've got 2 nitrogens that each want 3 bonds. So first bond there. But now you've got each nitrogen still wants to make 2 more bonds. Each nitrogen still has 2 electrons there that it would like to share with another atom. So what do? They share them with each other. And so you end up with a triple bond with 6 shared electrons. Okay, so you can have single bonds, most common obviously, double bonds or triple bonds.